Michael, you want to make sure? Okay, thank you everybody. This is part 2 of R plus Hadoop. We have a panel on Resolve, Traditional Statistics is Dead. And I have to admit this is a bit of a misleading title. It was meant to provoke. Of course, statistics is very, very important and all of us need to know statistics. However, there are some concerns about statistics in terms of its misuse, both intentionally and unintentionally, and as well as using statistics as you deal with larger and larger data sets. We're very fortunate tonight to have a wonderful panel of data scientists. All of these folks are super smart. We have Michael Malik on the far end here, Theodore Van Ruy, Nancy Abramson, Joseph Rickert, and Mark Labovitz. I'll tell you, Mark Labovitz has forgotten more statistics than most of us will ever know. I'll tell you a funny story about Mark. I got a phone call about a year ago when the data science media group was really small. And Mark says, hey, I'm a member, but I have some ideas about what you guys should do. And I said, oh, okay. It was very small, and I didn't really have any great ambitions. And so we went out to lunch, and we talked, and Mark had incredibly good ideas, things that I didn't really even think of. And one of the ideas, he said, we should go to the University of Colorado at Denver. I'm a professor there. We, will attract more people. It's a great location. We can go to Old Chicago afterwards. And it turns out that Mark's ideas were really, really good. And we all should really thank Mark for setting me on the right path, and we are where we are today in no small part because of Mark, so thank you, Mark. Okay.
If you don't like it, you can throw fruit. I mean, as long as it's fresh fruit, I can use it, to be honest with you.
The truth of the matter is that data science uses statistical and applied probabilistic knowledge to help determine if something is true, false, or anecdotal. And all data scientists should have a solid graduate level education in the use of statistics. So statistics is really used for risk-taking in making decisions. A lot of our clients are executives in big, mid-sized, small companies who need to use data science and to a lesser extent statistics to measure risk when they're making their decisions, to measure probabilities. And if you're going to be a modern data scientist, you have to learn to think probabilistically, not only with executives and companies, but with policymakers. Yet statistics can fool you. And today I'm going to go over some examples of how statistics can be misused, how statistics can fool you, and I'm going to ask some tough questions of our panelists. They'll be tough but fair, and all of these panelists are really expert statisticians and data scientists, so to level the playing field a little bit, I'm going to represent more of the decision maker, the executive, the policy maker, who needs to use the data science, use the statistics to make better decisions. Statistics can create an illusion of reality. I see this every day, and we need to be really, really careful as data scientists to make sure we do not create an illusion of reality for our clients. It can even bankrupt the financial system. The use of probabilistic methods for the estimation of risk, value at risk on Wall Street, or VAR for short, blew up the financial system. And we're going to talk about that in a minute. But I'd like to first have each of our panelists state their name, tell the audience a little something about you, and then for 2 minutes, I'd like you to give an opening remark, and I'm going to time you and hold you to 2 minutes. So Michael Malik, could you please start?
I'm a software developer for most of my life. A year ago, I was thrust into the big data world, and so I do some data analysis using R and IPython notebook, but primarily a software developer, so I'm sort of an observer, a trend watcher in contrast to the real statisticians on this panel. But you may have seen some of the links I posted to the comments on this meetup where we have the president of the ASA herself saying that, you know, maybe the statisticians haven't been paying attention enough to machine learning and big data, and maybe traditional statistics doesn't scale up well enough. And I think that's sort of the most direct and obvious theme from the title tonight, that, you know, maybe statistics can't scale, and maybe that's why it's kind of dying. Maybe that's why we have machine learning. But in my opinion, with machine learning, we need statistics even more, because, you know, we say that the role of a data scientist, the first thing they do is they explore the data. Well, by merely exploring, they're creating multiple models, and they're not necessarily applying like the Bonferroni principle properly, where they're immediately throwing out things that don't correlate, and they zero on the one thing that does correlate, and they end up with a spurious correlation. But you can avoid that if you apply statistics properly, and it goes right into this code of conduct that we're trying to apply with the Data Science Association. You need to apply these models and machine learning responsibly by applying statistics to the machine learning.
My name is Theo Efrain, and I am a practicing consultant in data analytics. I run a small consulting firm, Royalty Analytics. I also work for a company up north, Lafayette, called Cardinal Peak Engineering. It happens that I actually I've been coming to a few of these meetups. I met Michael, and then about a week ago, I turned up right in front of him, desk right across from him. So it's kind of a small world. And we looked at each other and we thought we knew each other. It took a few minutes. Oh, okay, I know where you are, where you're from. So, small world. The line that I take on is statistics dead. I'm not really sure that statistics was ever really that popular to where you say it's just a really great crime subject. So is it dead? I don't know. But it has really been replaced, I think, the last couple of years by the term big data. And I think a good part of the reason has to be that storage of data is very cheap. Computing power is very cheap. And so it's very tempting to replace really good thinking with overwhelming computing power. In fact, I read a blog post recently that was called Overwhelming Analytics. And the guy claimed that his best method was get as much data as possible, as many computers as possible, throw as many models at it as possible, and see what comes out. You know, it'll be the answer. And he apparently won some competitions that way, so he had credibility. You know, and I found that sort of a troubling trend, because in the end, what I think happens is you get overfit analytics, you get very spurious conclusions. When data tends to be close to random, if you look long enough, you can find a pattern that makes sense in the data. And applying that going forward probably won't hold up. So statistics, I feel the main role of statistics is to find uncertainty in the data and to figure out where we won't be able to use the model in the future.
Hi, I'm Nancy Abramson. I'm a data scientist for Spot Exchange, which is a real-time internet auction company for advertisements. And I'm coming from yet another perspective in that I started out as a database administrator, had touched with statistics back in the day, and also have come from BI analytics. What I've been doing is actually bringing data to business users in very simple, relatively simple ways compared to all the algorithms people are talking about, and letting the business users use the data in order to manipulate it and pivot it and understand their business better through KPIs and dashboards.
Well, I'm Joseph Rickard from Revolution Analytics. I'm a data scientist and our community manager for Revolution. I've worked in a number of different careers in different industries in my career, most of them having to do with quantitative ideas in some form or another, building models, sometimes quantitative marketing models. Immediately before I started with Revolution 3 years ago, I was working as a statistician for a healthcare economics company. So regarding this debate, I think that where we should start is to dig deep and ask yourself what you think a probability is. I don't think that the essence of guiding your way through the kinds of questions that are being considered here have to do with any of the details of statistical methodology. I think it has to do with uncertainty and the quest to understand uncertainty. So do you think randomness is a property of the world? Are you the kind of statistician that believes that probabilities are really some sort of relative frequencies? Do you believe that uncertainty comes from a lack of knowledge? Are you the kind of statistician, maybe a Bayesian, who thinks that the uncertainty in the world is due to our limits on our knowledge? So when you're approaching any of these kinds of problems, the amount of data only complicates things, I think. But the real way to start your investigations is to go to first principles. Think about what you mean by uncertainty, what you think the consequences are of your decision, and to work with tools that help you on the main line to answering your question.
My name is Mark Labowitz. I have a very checkered career. Truth be told, I'm not a professor here at the university, I'm a lecturer. So don't confuse me with one. Presently, I do consulting for a healthcare business company in Philadelphia, and good deal of my background is in financial data analysis. When I heard the topic, I thought to a great extent that the proposition, I thought it was silly. I still think it's silly. I think when I say when you say traditional statistics is dead, Fisher's dead, but analysis of variance done in 1918 is still very much alive and used continuously. L.H.C. Trippert, who did his work on extreme value, generalized extreme value theory in the 30s, is dead. But generalized extreme value theory is very important in a whole bunch of fields. Carl Friedrich Gauss is dead. But I can tell you least squares is a very important algorithm that's used in a lot of things. John Tukey is dead, but visualization of statistics, of data, is very important even today. And of course, Reverend Thomas Bayes is dead, but we wouldn't go without it. I mean, the only person who I think who's really has a major breakthrough in statistics, most important, that's still alive is Bradley Efrain, who developed bootstrapping, and maybe that's the only solace we can take, that he's alive. The point of the matter is that you're dealing with uncertainty. There is no such thing as big data that's going to get rid of uncertainty. Uncertainty exists in the universe, and how you're going to deal with it, it doesn't matter. You're still going to have to deal with it, and that's what statistics is about.
Oh, that was excellent. Okay, yes, it is about uncertainty, but can humankind manage uncertainty? Not that we can defeat it, but can we learn better techniques to manage uncertainty, to understand risk, to make better decisions? And I want to start with the concept of risk, value at risk, which is a Wall Street term that built statistical models attempting to manage financial uncertainty. And in a nutshell, what VAR purported to do was to say on any given day, a firm has exposure to X number of positions and can only lose Y amount of money. Now you can see up on the screen, this is the basic VAR model, and this was thought to be gospel on Wall Street for over 25 years. Now, it purports to be very precise, but the problem is that the assumptions embedded in this model are very, very wrong. And I want you to look very, very closely at the tail end here, also on the front end. You see that VAR basically deals with the distribution in the middle, but you have to worry about the tail end. And in a nutshell, decision makers relied on this VAR model, which were very flawed, and it gave them a false sense of security to be able to make decisions, specifically to borrow money, to use leverage, and to engage in certain trades that had certain risk profiles, especially at the tail end, that this statistical VAR model did not show. So the question is, and this is for the panel, and anybody can volunteer to answer, and then others can jump in and respond. Number one, are tail risks measurable scientifically? And if the answer is yes, how would you use statistics to measure tail risks? Somebody want to take that?
Yes, Mandelbrot showed how to measure tail risks. His work that dates back to the 1920s. There's been a lot of good modeling and stochastic processes in that area. Some of you've heard of fractals. And so there are a lot of good Brownian motion models. There's a number of excellent mathematics done in that area. The fact that not everybody on Wall Street was conversant with these things is a different matter. But there's some good work in that area, and in fact, I think the way to go about learning more is to look at the work of the Stanford, Bradley Efrain was mentioned here, the statistics department and the probabilists at Stanford published a lot in that area.
I think so much of what you're saying is, it's wrong at so many levels that it's naive. A value at risk is just a measurement of a quantile. It says if you have a distribution that you understand, let's leave aside the fact that this distribution is time varying, which is going to make your VAR varying all over the place. But all it is a quantile, and says that I want to know what is the boundary of the 5% of the tail. I would first of all doubt that it was the major thing that brought down Wall Street. Let's look at AIG. Let's look at the failure to deal with default swaps appropriately. That had nothing to do with VAR. That had a lot to do with illegal activity. In AIG being able to underwrite much more work than they could possibly afford to pay out under any reasonable insurance approach. There is considerable amount of work in extreme value theory. I think that you're misleading if you're not reading the Basel reports on what is the various types of stress testing. VAR is not the element that you use in stress testing for organizations. Chase was not just fined $12 billion because they used VAR. I can tell you that. They were, cheating is rampant, and if you want to blame it on VAR, go right ahead. But don't look at Jamie Dimon at all. I mean, that can't possibly be the situation.
Does anybody else want to jump in?
So I've actually been working with a company in Houston recently, over the last couple of years, helping them to develop risk models for specifically related to IT security losses, which IT security is, and specifically when it comes to losses, very sparse data set. I mean, there isn't a lot out there to help quantify that. So there's two things that I always keep in mind when actually talking with executives who are making decisions on things. First of all, 95% confidence interval, or the 95% demarcation line, is where the losses start. It's very easy to interpret, and this is sort of the naive understanding of the statistics, that 5% of the time I lose X amount of dollars. And so therefore, okay, I'm willing to take that loss every 20 years, is what they kind of think to themselves. But that's where the losses start. Theoretically, that tail end can go off to the right or the left, whichever direction you want to call it. It can go as big as you can imagine. The second thing is, okay, the VAR models that are being used perhaps are not realistic. What if we expand the tails? What if we use a distribution that looks a bit more like reality? Are you now willing to take this risk? So yes, the models are not perfect. However, using some statistical understanding and I think illustration specifically, your losses could be very, very large, not just the 95th quantile. That really helps actually drive the point home.
Okay. Thank you. I want to move on to another topic. By the way, there's a lot of debate. I'm not sure that there's any right answer. There are many people who argue that VAR is seriously flawed and that perhaps tail-end risks are just scientifically unable to be analyzed appropriately. I know hedge fund traders who say VAR is totally flawed, would not rely on it, and that there may be a statistical model that would help us manage risks on the tail ends or severe rare events. We just haven't found it yet. But there are also others who claim that VAR is fine, that most of the problems that happen on Wall Street really didn't have anything to do with VAR. Yes, it doesn't cover a lot of areas. It's flawed in some different areas, but you're making much ado about nothing. So we'll have to continue that debate another day. But I want to move on to the concept of statistical significance or statistical insignificance. I run into this all the time, and I want to point out a paper from 2005 by a doctor at Stanford University. His name's John Ioannidis, and he published a paper showing why, as a matter of statistical logic, the idea that only one person in 20 or one paper in 20 gives a false positive result is hugely optimistic. He basically argued that most published research findings are probably false. And he's gained quite a following, and he's highly respected and well regarded even within the medical community that he so severely criticizes. What he asserts is that the customary approach to statistical significance ignores three things. One, the statistical power of the study as measured by its ability to avoid type 2 errors, false negatives, in which the signal is missed in the noise. Two, the unlikeliness of the hypothesis being tested. And three, the pervasive bias in favor of publication of claims asserting to have found something new. So a statistical powerful study is one that's able to pick up things even when the effects on the data is small. In bigger study, where you can run the experiments many times, recruit more patients for a trial, they're more powerful, and they create, you can find more accurate, more meaningful results. So a power of 0.8 means that the often true hypotheses tested, only 2 will be ruled out because of the effects are not picked up in the data. And this is widely accepted as powerful enough for most purposes. But this is not always met. In fact, big studies are more expensive, and often they don't design or run the studies big enough. So a recent study by Ioannidis and colleagues found that in neuroscience, the typical statistical power is only 0.21. and that in that field the average power is 0.35. So he argues in his field you might expect 1 in 10 hypotheses to be true. In exploratory disciplines like genomics, which rely on going through huge amounts of data and trying to find correlations and causality, you might expect just 1 in 1,000 to prove correct. So if you consider 1,000 hypotheses being tested, of which 100 are true, studies with a power of 0.8 will find 80 of them missing 20 because of false negatives. Of the 900 hypotheses that are wrong, 5%, or about 45 of them, will look right because of type 1 errors. So add the false positives to the 80 true positives, and you have 125 positive results, fully a third of which are specious. So if you drop the statistical power from 0.8 to 0.4, which seems realistic for most fields, you still have 45 false positives, but only 40 true positives. So more than half of your positive results are wrong. Meaning, in a nutshell, most of the published academic research out there is nonsense. It's absolutely wrong. Let's look at this chart. This chart shows very, very clearly that you have so many false negatives and false positives, and it goes up exponentially with the larger data sets, that what you're going to find are true, real correlations in the data with causations, and that yield positive results is just a very, very, very small amount in the research. So really the negative results are more trustworthy, even in the case where the power is 0.8 and there are 875 negative results, of which only 20 are false, giving you an accuracy of over 97%. This is incredible. I mean, what he's basically saying is that, I think he did research on 100 different medical studies, and he could only do 6 out of 100 replications, only 6 to be replicated. Meaning most of the research out there is absolute baloney. And what bothers me is that the future data scientists are learning from academics who conduct this type of research, which are most academics. And our leading journals are publishing this malarkey. So I would like to ask the panel, how would you, as a professional statistician, deal with these problems?
Well, it's news to me, but it doesn't surprise me. I mean, I think that number 3 bullet from a few slides ago, that there's a tendency to want to publish something new. You don't want to publish a bunch of negative results and have that to your name. That's kind of interesting, because that's not even going into the realm of machine learning. It's just old line statistics, but just the cherry picking, the bias toward trying to find a correlation, and you'll eventually find some correlation, but you're not balancing it against all the negative trials that you're ignoring and not publishing.
Is this an indictment of statistics or an indictment of the principal investigators and the way they do stuff? Data analysis sucks, generally, and the point of the matter is that research is climbing molehills, okay? It is patently clear that there are methodologies, as you're pointing out, and Professor Ricketts or Dr. Ricketts or whatever Joe said. Joe has indicated that methods in cross-validation, and there's a lot of techniques that would allow you to cut this down. But I'll throw a question back at you. You threw a lot of very pejorative phrases at people. Do you think that they really are doing this on purpose, that these are errors of commission, that they're trying to mislead? Is that your... So they're dishonest. So as a general rule, they're dishonest.
I think it's a little I'm the moderator. I asked the question.
Well,
I'll answer this once, but no others. And the answer is, I think very few intentionally do it to mislead. I think that there are perverse incentives within the system to publish
No doubt.
incredible results, and there is not enough peer review or honest peer review or self-correcting mechanisms within academia to catch a lot of this stuff.
Well, that's an indictment of society, not so much an indictment of statistics. I mean, yet your topic is traditional statistics is dead. Maybe traditional publishing is dead. Maybe that's the topic should be.
I would like to say that one way that I've heard is to make data sets that are used in publications public, so that they could be interrogated by other people. And that would, I think, bring some more integrity into the system.
Yeah, and along those lines, R has a great facility to publish all of your conclusions, the work that you did to get there, and the data set all in one go. So.
All right, so what we're talking about there is reproducible research. And it is true that a great number of medical studies that are published can't be replicated. It is true that it's difficult to get hold of the data sets. And it is true that if you look through the methods section and you're a statistician for many medical papers, you just start to cry. So, in fact, I think where this is going, all of you eventually are going to need health care for yourselves or for someone you care about. And in this day and age, you want a statistician on your team. You want somebody that can read the medical papers and ask your physicians, as they're reading the papers, and not stop at the surface level studies show. So you do need to have the ability to interrogate. And it's very positive, as mentioned here, the big movement within R is for reproducible research. If you have at all interest in it, I encourage you to go to the R Studio site and look at the knitter packages. And what you can actually do is build live documents. So you just don't build a PDF file, you build a document that has code embedded. You change your data, you change your code, the paper changes. So that's one vision for keeping science honest and accessible. The other point I'd like to make is that you seem to be indicting academia, and as a whole that's unfair, especially with regard to a particular thing like statistics, because there are different traditions. I mean, what you find taught and worried about in the statistics department is different from what happens in the political science department. There are whole generations of people now who don't read each other's papers. There's not enough of that going on. So one of the things you need to do, we talked about two cultures before, of data science and statistics. Well, even within the traditional, before you leave out the data science, there are many cultures that need to read each other's papers. I think that the third thing, you spent a lot of time talking about test of significance. I believe that the test of significance have basically seen their day. That the way forward, especially when there's lots of data available, is to think about confidence intervals, making estimations, and measuring the uncertainty in your estimator. It's not so much thinking about, you want to run a test, and then you're going to run your life on whether or not there's a p-values of a certain value or not. So those kinds of things, the Neyman-Pearson theory is incredibly useful in certain areas, but I wouldn't use that as a model going forward in this different kind of environment where we have so much data.
Okay, I'd like to move on to statistical overfitting. Theo, you mentioned overfitting, which is a huge problem in statistics and in data science in general. In statistics and machine learning, overfitting occurs when a statistical model describes random error or noise instead of the underlying relationship. It occurs when the model is excessively complex, as having too many parameters relative to the number of observations. A model which has been overfit will generally have poor predictive performance, as it can exaggerate minor fluctuations in the data. The danger is that you see relationships that really aren't there. The best example of this is the Super Bowl and related to the stock market example from 1967 to 1997. If an original National Football League team won, the stock market was up an average of 40% per year. If the new league, the American Football Conference team, won the Super Bowl, it was down by almost 10%. I think this happened 28 of 31 years. And here's the statistically significant fact. Any standard test of statistical significance, if taken literally, would have implied that there was only a 1 in 4,700,000 possibility that the relationship had emerged from chance alone. So models can be tuned in many different ways that give researchers more scope to perceive patterns where none exist. It's one of the flaws of human beings, myself included. We tend to see patterns when there really aren't patterns. I have a theory about this, by the way. I think that when we were hunter-gatherers, our minds were trained to see patterns because if we saw a lion running across, we had to develop the ability to hide and protect ourselves for survival. But now that we deal in this highly abstract technical world, that same cognitive ability really hurts us. So according to many estimates, three-quarters of published scientific papers in the field of machine learning are absolute nonsense because of this overfitting, according to Sandy Pentland, a computer science at MIT. And Sandy is very well respected. He doesn't just shoot his mouth off. He knows what he's talking about. So the question is, as statisticians, how do you recognize and prevent statistical overfitting?
It's pretty simple. You don't keep building the model over and over again on different subsets of the data until you get something that looks good. The more you do it, the more likely you are to overfit. So there's really no way to do it but to not use your data, or to use your data as less as possible. That's my short opinion.
Set aside a set of data for validation. So you develop your model, then run it on a reserved set of data to see what kind of results come back, and that helps prevent overfitting as well.
You may need some kind of log. I mean, when you're, quote, exploring this data, keeping a log of everything you've tested and everything that failed. I mean, going back to your NFL example, I mean, they probably tested against the NHL and the NBA or, baseball and all these other leagues, and, they didn't see anything there. Well, you need to take into account those negatives when you calculate your probability. So it's almost like you need maybe a clean room where you have one data scientist that does the exploration and data cleansing and then hands it over into a clean room where somebody actually logs all their activities.
All right, so this gets at the very essence of why the classically trained statisticians think the term data mining is so pejorative. So, first off, what's data to begin with? In some sense, for the classically trained statistician, you don't have data until you first articulated your question, decided on your experiment, designed your experiment, designed how you're going to analyze the data, and then draw the data. For some people, data only happens after you've put together the analytical structure ahead of time. So when the world is flipped and people ask you, they give you data for which you don't know its provenance, you don't know where it came from, you don't know how good it is, you don't know how clean it is, the job of the statistician becomes the dirty work before any kind of inference happens, of trying to clean things up. You have to make sure that you have something that's worthy of being analyzed and for which you would stand by its conclusions. Now, overfitting is really a simple concept. If you have 100 points, 100 observations, and you build a model with 100 parameters, you can fit it perfectly, an overfit model. So there's always been in statistics this idea of parsimony. You want to build the simplest models possible based on data that you understand and control, that you had, you know the provenance, and that you can trust to be able to have some predictive power. Now, classically, I think what we do now is, as what's mentioned over here, when you have a large data set, typically what you do to avoid overfitting is to take subsamples. So you fit the model on some small proportion of the data, and then you test it on other data that have not been used in building the model. So that's the best practical way that's been devised so far to avoid overfitting. So some sort of cross-validation.
Observational data, which is what data that's given to you, has or frequently has a great deal of problems with it that you have to deal with, and you have to do a lot of work as a statistician. When you get observational data, if you look at your time budget in terms of the amount of work you have to do, my experience is that 65% of your time budget is just spending cleaning the data, looking at it, trying to figure out if it will meet any standard that you can do work on. Maybe 15% is model building, and the rest of it is in back-end diagnostics. So you're basically a data pathologist when you're dealing with observational data, and you're trying to figure out what's there. Also, there are lots of little things little quirks in observational data. I mean, the quality of teachers in Britain was directly related to the amount of beer they consume. That's always been a result that you can look at. But when you're dealing with essentially time varying phenomena, such as you're talking about with the NFL, the old expression that past results are no guarantee of future performance, you ought to put that on the bottom of your prospectus and deal with that analysis.
I think that's an SEC rule for most mutual funds.
It's also on every television commercial that you'll see.
Okay, I want to move on to the danger of statistical models. All models are wrong. All models are wrong. I'm the decision maker. I would never ever rely on a model alone to make a decision. I would use it to try and help me understand a phenomenon, a situation, a concept. But only a fool would make a decision based on a model. Why? Because all models are wrong. But some are useful. Who said this? George Box, the very influential statistician. The danger I see today in data science is too many data scientists are coming up with stuff, building these models, which are beautiful. They look beautiful, beautiful visualizations, beautiful logic behind them. The only problem is that they're dead wrong. They're an illusion of reality. And I would never let one of my clients rely on them. And I've had to fire people because they've created beautiful data models that have absolutely no resemblance to reality. This is very, very dangerous. I see this all the time, not only in academia, in research, but in economics it's prevalent, and it's seeping into the real world where we have executives and policymakers that have to make real decisions that influence real people. It's very different when you're making a decision that's influencing real people compared to making debates and moving data around on a computer screen in a model. So what I worry about is, are we using models of uncertainty to produce certainties? So the central lesson that we get in real life, as opposed to playing with data on a computer or a statistical model, is that the exposure or the payoff that creates the complexity. It's the opportunities and the dangers. It's not the knowledge. It's not the statistical distribution, model representation. So, for example, in finance, in some areas you could be wrong and turn out okay. You lose a little bit of money. In other areas, you can be slightly wrong and explode. You can blow up. So if you're leveraged, if you're highly leveraged, small errors can blow you up. If you're not, you can lose a little bit of money and enjoy life. But you're never going to get this from a statistical model. Again, this is real life. You're dealing with real money. And this proves to you, or proves to anybody who becomes a hedge fund manager or a trader, that you have to be very, very, very careful about relying on statistical models. So, let's look at the anatomy of a blow-up. Here, look at this, statistically significance. You can have all these years of making money. You can make a profit for 50 years. You're a bank, okay? Make a profit for 50 years. And all of a sudden, there's a tail-end rare event that your little model did not foresee, and you blow up, and you lose more money than all the profits that you've made. I've seen so many hedge funds blow up like this. I've seen financial advisors who make money for their clients for 20 years and then blow up, lose everything, and then more. And most of them relied on statistical models. Okay, so here's another example. A turkey is fed for 1,000 days, okay? And every day, you confirm this to the statistical department over here, that the human race cares about the welfare with increased statistical significance of the turkey. But on the 1,001st day, the turkey has a surprise.
It's usually 364. It doesn't run 1,000 days to Thanksgiving. You must have a little bit of, it's usually 364 days. The joke is usually told that way. And then on 365th day.
So,
it's usually a good joke.
again, the turkey has a surprise, okay? And it's statistically significant. You know, you would look at the statistical model here and say, oh, the turkey doesn't have anything to worry about. Well, all of a sudden, boom, we have Thanksgiving. The turkey's dead.
Look at statistical
Yeah.
significance that way, but I would.
Well, I think the point stands, and I'll let you rebut it and comment on it in a minute. So let's look at another graphic here about IndyMac's annual net income. For so many years, it was making money and gradually increasing its income until one day, of course, a rare event came and boom, it blew up. Now, you've got the smartest statisticians on Wall Street, okay? These are people with the best credentials who created the models that these firms worked under, okay? So this wasn't, Joe Blow from the University of Colorado who just got a PhD in statistics. These guys were the creme de la creme in the finance department, and they come from the best universities, had the best degrees, and produced these statistical models that everybody said, whoa, isn't this beautiful? Let us run our entire financial system according to these risk scenarios. And everything worked out real well for many years until, boom, you had a rare event. So you see that graph that I just showed you represents the fate of close to 1,000 financial institutions. So the banking system bet against rare events. In other words, these statistical models did not consider these tail-end rare events. If they could have, they would have.
No, they did consider the rare events.
These are the
They
best
did.
science. Well, the argument is that scientifically
No.
you can't.
No,
If you
that's
had,
not true.
I would suggest
That's not
you
true.
go to Wall
It's
Street and make a lot of
uncertainty. You're
money.
not,
it's not true.
So anyway, I'll give you a chance to state in a minute. You can go to Wall Street and make millions of dollars if that were the case. So these companies lost over $1 trillion, okay, on a single error, more than it was ever earned in the history of banking. All right, these are the best and brightest. These are the data scientists of the financial world. Now, the bankers kept their previous bonuses, and it looks like us taxpayers, us citizens, are going to have to foot the bill. That's a huge agency problem that we have that we need to cure in finance, just as an aside note. So again, can any known statistical method capture the probability of rare events with any remotely acceptable accuracy, except of course in hindsight? And go ahead, I'll let you elaborate.
Well, first off, a statistician will tell you rare events happen. You know, they'll tell you that if they build a model and you're looking for a 1 in a billion event, that doesn't necessarily mean that the next flip of the coin won't be that rare event. Everybody who builds models and characterizes uncertainty is competent, knows that. Most of the models that have been built, even from the beginning of statistics, have been concerned with rare events. Pascal, who along with Vermont, who did the first probabilistic modeling at all, is famous for Pascal's wager. Everybody know what Pascal's wager is? His point was that should you behave in a strictly religious way or not? And the point was that he thought that you should follow the precepts of his religious beliefs very carefully, because even if there was one minute chance, a rare event, that there was a God and a hell, that the risk involved and the consequences were so great that he gave up doing probabilistic modeling and decided to live that way. It's been a question since the beginning of probabilistic modeling that's been on the minds of people who characterize uncertainty. Now again, you started off by talking about models being pretty but not representing reality. Well, we all build models. No one has the ability to apprehend reality in its suchness.
That's pretty deep.
It's deep.
It's true.
And that's what it's all about. What is it? We build models of the real world. We're building models right now of what we're seeing. What our brains are working right now to model what's happening next. All of our thinking is in terms of some sort of model, some of them more formal than others. But I think the great point is that building models or understanding to think about uncertainty is not natural. We are engineered to see lines in the jungle, and we're engineered to be able to catch balls without thinking. But it's very difficult for people to think about probabilities. It's very difficult for people to have the discipline to think about important decisions and using the probability calculus. So it's not natural to us. And I think one of the things that we're entering now in this world where data are so available is that we're all being dragged into this to think probabilistically.
But I guess the question is, do you know of any statistical method that can capture the probability of rare events with any sort of accuracy? That's the question, yes or no?
Yes, the normal distribution captures the
It doesn't say that the next event is not going to be that event. It only says that in the long run, potentially, you're going to have that event. I mean, if you have risk, Michael, if you have risk, then you're going to... I mean, once again, I'm going to turn back to you. What in the world are you proposing as a model for financial people if you know that these models suck? You're saying the models suck. You're saying you can't trust them. You're saying that sometimes the relationships in terms of diversification go haywire, which is exactly true. They demonstrate the haywire. What model are you proposing?
I'm not proposing any model. Number one, I'm running $1 billion of my client's money, and I'm hiring you as a consultant to come in to help me manage risk and understand reality, so I can make decisions on how to allocate
And
my
if you don't want to,
client's resources.
if you want to stop, if you
Stop.
want to
Stop.
not
You-
do as much money, if
If
you want to
you
make
don't
not much
give me-
money.
Hang on. If you don't give me models that help me understand so I can make better decisions to more optimally allocate my resources, you have not provided any value to me as a decision maker.
I can give you
I
plenty
don't
of
create
models.
value.
I can give
I
you
don't
plenty
create
of models. It's a matter of how greedy you are. That's exactly the case. You can be less greedy. We can set up models that protect you in some sense, but not guarantee protection against various downsides. That you have to pay premiums for those sorts of things. You have to pay insurance policies essentially, and you're not going to make as much money. So you may not make your bonus that you have this year, and that's just going to be a problem.
But with all due respect, I think you're evading the main question that I have. Is there any statistical method to help capture the probability of rare?
Yeah, you can
rare
estimate
events with any-
estimate the probability. You can estimate it. I mean, that doesn't mean it's going to be. First of all, it's an estimate. It doesn't mean it's going to be.
Well, Michael, if you're asking, is there any model to predict the future? No.
But that's a straw man. You're saying I'm a straw man.
No, I'm not. I'm just saying, if I tell you, we'll put, I'm going to flip a coin. I have a magical coin here. It's not fair. There's one chance in a billion that it's going to turn up heads. Will you bet your life on it?
So, Mike, I think you're asking slightly the wrong question. Mark keeps saying, and I think he's right, that you can construct models that capture the accuracy, the accuracy, that accurately capture the probability of rare events. To the degree that you can capture any rare events being rare, it's hard to know exactly how frequently they're really going to occur. But I think when you're talking about finance specifically, the bigger question is not how accurate are the models, it's how much risk you're willing to take on. And if you don't start with likelihood. And actually, and I'll tell you where I'm coming from in this. I worked for Sallie Mae in 2008, and I lost my job because of models and because of the financial system.
Thank you. That proves my point.
That doesn't prove your point at all. That just he flipped the coin and it came up tails, and he was cut off. That's
I did. I was an IT project.
right. Okay. He flipped the coin and it came up tails, and he lost.
Let me finish. You don't start in finance with the question of how accurate is my model and what are the likelihoods. You start with the question of downside. What's going to happen if the worst thing happens? And is that acceptable to me?
Yes.
If the answer is my firm blows up and everyone loses their job and all my clients lose all their money, it doesn't matter how unlikely the event is, unless you have to take it for some reason, take that risk for some reason, which you really don't in any reasonable scenario. You don't take it. You don't sell 1 million calls because your exposure is limitless there, right? Regardless of how sure you are that the stock isn't going to go up a lot.
I don't disagree with any of that. I think I'm talking about something else. I'm talking about the limits of statistics, and I'm trying to get you to admit that there are some limits to statistics that you don't want to admit. Now here, let me give you an example. Let me give you an example. Maybe you're right. I agree with you. I think you make an excellent point. I think, Mark, you also make some excellent points, but I'm getting at something a little bit differently. In terms of measuring risk, I don't think it's that simple. You and I can reasonably disagree about what investment a level of risk would be. I may be a better manager of money than you because my interpretation of risk assessment is more accurate to reality than yours.
About likelihoods. You're still talking about likelihood. What is the maximum price of a stock? It is infinite. Okay, let's just say it's infinite, right? A stock can theoretically go up forever. If I sell a call on that stock, give someone else the right to buy it from me at a specified price, my exposure is directly related to the price of that stock. If that stock price can go up infinitely, my exposure is infinite. We can disagree about the likelihood of the stock price going to an infinitely high level, and there's a lot of room for disagreement on that.
You're talking
But
like
the
those guys.
exposure-
I understand what you're
But
saying.
the
You're talking.
exposure is a fact.
Let me
My
suggest
exposure
something
is
to you.
infinite.
You guys remind me of the guy on the infomercial who says, I've got this stock picking system that's built on statistical models, and if you follow it, you invest your money,
People who invest in stocks and people who do this are gamblers. It's fundamentally being a gambler. You're going to take a risk.
What's
And how
probabilism if not a form of gambling? You're taking risks.
Well, okay,
It's
sometimes,
probabilistic.
and sometimes you bite, sometimes you eat the bear, and sometimes the bear's
No, but let's get back to
Seriously, I mean, what are you expecting?
Let's simplify this. I run $1 billion.
Okay.
I'm the decision maker.
Okay.
You need to provide me with statistical models that will help me make decisions to better manage my clients' money. Everything else is baloney, okay? Now, you either provide me with good statistical models that help me make better decisions, or you're fired.
Then you would be fired.
No, what you want is predictable quarterly gains. You're not willing to take the small quarterly losses for the big gain down the road. The exact opposite of your graph.
But you don't know that that's going to happen.
It's your indie math
It's
graph, but in
asset
reverse.
allocation.
No.
I need to make decisions on where to allocate assets. Now, I need that there are certain risks. There are 100 different models that reasonable people can assess risk differently on. I'm really worried about the probability of rare events, okay? And I suggest to you that statistics has not evolved yet. There's a limit to statistics. It's not evolved as a professional discipline to be able, with any acceptable form of accuracy, to be able to capture the probability of rare events.
Do you know anything about extreme value theory, Michael, or generalized extreme value
No,
theory, or anything
but-
like that?
but-
Well, then you're really not saying anything at all here.
Look.
I mean, you can estimate these
Look,
things.
you're
that
fighting.
I mean, yeah,
You've
I mean,
given
so
me
Donald
nothing to
Trump
help
is
me.
here, and we
You've
were
given me nothing to help me make my decisions. That's what
That's
data
not
science is
true.
about.
That's not true. You've given you something, but I can't guarantee the future.
Michael, you keep telling them, they're fired and this and that, and I understand that, and I think you actually do make an interesting point. To some extent, the statistics of the financial collapse are irrelevant. It was the decision makers who made decisions with the models they had, imperfect as they were. Maybe they ignored the blind spots, maybe they knew what they were, and they were chasing bonus. It didn't matter how good the statistical models were or weren't. It might have, in some cases, been simply irrelevant.
And the Super Bowl guys in the hot tub in Aspen laughing at us. His bank account's all the proof he needs.
Well, what I'm suggesting is that statistics can help us, but they can also create an illusion of reality. I think finance is one area that proves empirically that statistics and statistical models have certain limitations. And you need to be very,
Human
very
reasoning
careful.
has limitations.
What?
Human reasoning has limitations.
That's right.
Any kind of
Quantitative
reasoning.
precision doesn't
There
scale.
isn't anything to predict. It's random.
You're sort of approaching the problem as if there's a God out there, and God is going to eventually tell you the right answer because there's not uncertainty. God is just hiding the relationships from you, and the statistician is getting in the way and saying there is no God. I'm just saying there's uncertainty. That's a load of malarkey. I mean, that's
I think you're setting up a straw man.
No, you're setting up a straw man. I don't understand.
Let me respectfully suggest that all data scientists really do are help decision makers make better decisions. And statistics can be used in some areas it has its limitations. Machine learning can be used, building better algorithms can be used, using business domain, math, other areas can be used, but your job as a data scientist is to help your client, the decision maker, to make better decisions. And many times I see brilliant statisticians build beautiful statistical models that create an illusion of reality and that do not help them make better decisions. If that happens, you fail as a data scientist.
Michael, the
and you
only
may get
people
fired.
who mistake the models for reality apparently are the decision makers.
Yeah, exactly. Exactly.
And I do think, honestly, I think there is a level of learning that needs to be done at the decision maker level, because I deal with a lot and trying to educate them and have them come up another level so that they can use data to make better decisions, because they certainly understand my business much better than I do.
Let me just finish off with one last question and then we'll end it. There appears to be a need for innovation in statistical methods, especially for working with large data sets and finding valuable, actionable insights. Do any of you have any suggestions on how we can create a climate where statistics is able to innovate and progress further than where it currently is?
Yeah, I would say that I really like the RStudio, the Revolution, the reproducible research movement. there's so much in the open source world with GitHub and being able to publish your work at any time, being able to publish your results at any time and have anybody look at them and critique them. And basically the speed at which development is happening in the statistical and statistical computing world is so fast that I think that's just a very positive thing, and that's what's going to really push it forward.
Yeah, I would agree with that, and the whole kind of crowdsourcing, open source movement that's going on right now. Just
Well, I think they can provide a tool, but it could also be a tool in the wrong hands where somebody inexperienced or unknowledgeable can push all these great new buttons in R. So it's a sword that cuts both ways.
One thing I will give you is that there's statisticians that have sort of failed, I think, to go in going into the machine learning world and starting to work in that world more with those new algorithms. I think there's a very large need for statistics to move into machine learning. I mean, I've been in situations in which people produce two neural networks from samples from the same data set. And there really is no way to decide between the two of them, or other types of machine learning, and there's not ways to decide between them. I think that's a really good area because machine learning algorithms are important, they've proved valuable, but they need to have the uncertainty that's in, then there is uncertainty, because anything working with data has uncertainty just embedded in it, is going to be an area where I think a lot of fruitful work could be done if statisticians were to turn that area.
Anybody have anything else? Anybody have any closing remarks? Thank you very much. Oh, go ahead, question.
Whether intentional or not, I think, so, and I'm kind of new to big data, I'm more on the decision-making side. I kind of came in just kind of trying to ask the question, sort of what is big data, what does it mean for a lot of different things, and I think what's really interesting about the discussion that just came out is that one of the biggest values of big data, perhaps, and again, I'm very new at this, but is not so much the new conclusions that can be found from all these data sets or new ways of finding conclusions, but that a lot of tools are now coming out so that folks like myself can better grasp, the uncertainty in decision making, and it's not necessarily somebody saying, hey, this is your uncertainty, but there are tools that allow me to interact with the data in a bit more meaningful way and understand what statistics are telling me rather than just having it be a number on a page.
Yeah, believe it or not, let me just say one thing. I don't think that there's a lot, I wouldn't say a huge number, but data scientists I've met who are statistics haters. And I guess, maybe they believe that Asimov's psychohistory is going to be eventually taken care of, and eventually we won't have to worry about statistics because psychohistory will write all the equations of human interaction. We just will find out about it. The only point is don't forget there was the mule in Asimov, and that threw an entire clipper into the situation. So there's always uncertainty, even in Asimov, there's uncertainty.
Any other questions? Thank you.